In the last lecture, we considered a circuit consisting of an inductance and a capacitance, in which the capacitor is initially charged. And what we found is that this circuit provides sustained charge and current oscillation with an angular frequency omega equal to 1 over square root of LC. The last thing that I take up in our discussion on alternating current is an application which is very important for practical use of alternating current, and that is a transformer. In fact, right in the beginning we have pointed out that one of the advantages of using an alternating current circuit is our ability to step up or step down such voltages. And so let's look at how does a transformer work first. So a transformer has two sets of coils. So let me first show it in one type of circuit. This is not necessarily the only type of arrangement that is possible. So this is a soft iron core. Now what I have here is this, that on one of the arms I have certain turns of wire which is put in. I will assume that to begin with there is no resistance in this part of the circuit, but there is an alternating source of voltage with an amplitude V primary. So this part is called the primary part of the circuit. We assume R is equal to 0. Now on this side, what I have are windings. We'll see that the number of windings depends upon what do you want to do with it. So let me at this moment keep it an open circuit. This will of course be connected to load. So this would be connected to load. So let me say, so this side is the secondary part of the circuit. This is called secondary. Once again I assume that at the moment load is not connected and the resistance of the circuit is equal to 0. Now look at what will happen. When an alternating current passes through the turns of the primary, it will produce an alternating EMF in the secondary because of mutual inductance. So alternating voltage in primary leads to alternating EMF in secondary. This is actually the basic principle of a transformer. It's because of mutual inductance effect. The role of the soft iron core is actually twofold. One is it will increase the strength of the magnetic field produced by the primary current. So soft iron core, what it is doing is so increase magnetic field strength. The second thing that it does is to help link the flux in the secondary circuit and make sure that it is linked to each turn. Help flux linkage. Now suppose phi is the flux through each turn of the primary circuit. Let me also assume NP is the number of turns in the primary circuit. Now notice, since I have assumed that the resistance in the primary circuit is equal to 0, which is an unphysical assumption, but let's stick with that right now. My voltage in the primary circuit must be exactly balanced by the back EMF, because otherwise the current will become unphysically large. So Vp is Np d phi by dt. Now if I assume that the flux linkage is tight, that there is no leakage of flux, which is again a slightly unphysical arrangement or assumption, then the same flux is linked with each turn of the secondary circuit. So therefore, my Vs is, if Ns is the number of turns in the secondary, it will be minus Ns d phi by dt, because it is the same flux which is being linked. So assume Ns equal to number of turns in secondary, and the no flux leakage. So if you compare these two expressions, you immediately get the ratio Vs by Vp is equal to Ns by Np. Now, this is the primary equation of a transformer, because it tells me that if I want the secondary voltage to be stepped up, meaning thereby secondary voltage to be larger than the primary voltage, so Ns should be then greater than Np for step up transformer. The reverse is true if you want a step down transformer, then of course Ns must be less than Np for step down. Now in an ideal transformer, what happens is the entire power is transferred to the secondary. So let me write down an ideal transformer. All power is transferred. That implies that Ip, which is the current in the primary times the voltage in the primary, must be equal to current in secondary times voltage in secondary. This is my second equation. Now if I compare these two expressions, this was my equation 1. Then what you find is this, that my Ip is Is times Vs by Vp, which is equal to Is times Ns by Np. So this tells me that I have an inverse relationship with respect to the turns in the current part of the circuit. So what we notice is that we have Np by Ns is equal to Vp by Vs and is also equal to Is by Ip. So what it implies is that supposing we are using a step up transformer, then increase in voltage would automatically come with a corresponding decrease in current. And conversely, if you are using a step down transformer, then the voltage will decrease, but the secondary current will increase. So there is a trade-off between the current and the voltage, and depending upon what our usage is, we have to worry about that. So let me illustrate these with some typical examples. Suppose I wish to melt a piece of nail which has a fairly small resistance. Let's take it typically resistance is, let's say, 0.004 ohms. Now I wish to melt it by connecting it to an electric circuit by providing heating effect of electric current. Now obviously I cannot directly connect such a small resistance to the mains. Suppose my mains is 240 volts, then the current that you generate would be 240 divided by 0.004, which is equal to 60,000 amperes. No household supply can take this larger current, and your the fuse, if it is there, or an MCB will trip. So what does one do? The current that I draw from the primary cannot exceed the typical household current, which should be within about 8 to 10 amperes. Now here I am helped if I use a step down transformer, and let's consider what happens if I use a step down transformer. Supposing this is 240 volt mains, I will work out what type of transformer do you actually need. So this is the secondary circuit which is connected to the resistance that we talked about. Now the way to do it is the following. I calculate using property of this piece of nail, like its mass, its specific heat, etc., and find out how much of heat do I need to melt this over a certain period of time. Now suppose I did that calculation, then my Q, that is the amount of heat that is required, is given by I square R times the time, which, let me take it to be a couple of minutes for convenience, and I can easily calculate how much current do I require, because everything else is known to me. Suppose the current that I calculate is, let me call it IS to distinguish it from the previous I. Supposing the IS that I calculate is, let's say, about 500 amperes. Now this is also a huge current, but remember, I am not drawing it from the primary circuit, from the mains. I am drawing it from a secondary circuit, and we'll see what effect does that happen. So then what I have is the following, that the current IS times RS, that's equal to, that's the secondary voltage Vs, that is 500 multiplied by 0.004, that is just equal to 2 volts. So I need a huge step down, and in fact you can see it, since this is 240, you want this circuit to provide you 2 volts. So therefore this is a step down with a ratio of 120:1. So that 240 is reduced to that. Now, so NP by NS, which is Vp by Vs, is 120:1. So let's calculate now how much current was actually drawn from the primary in that case. Now IP, which is the current drawn from the primary, times NP, that's equal to NS times IS. And so therefore IP is NS by NP, which is 1 by 120, times IS, which we have taken to be 500, and that you can see is a very reasonable value of 4.16 amperes. How much of power was actually delivered by the secondary circuit? So the power delivered by the secondary circuit is IS square R, and that's simply equal to 500 square multiplied by 0.004, and that's about 1000 watts. This is usually a good enough power to melt the piece of nail in, let's say, a couple of minutes. Now in practice, the power transferred, this is what I have assumed, that the entire power provided in the primary circuit is transferred to the secondary circuit. Now in practice this is never so. So let's look at what are the now what is the reason for that? So number one is that all the flux will not link to both the primary and secondary. This was one of our assumptions. So the flux linkage is not total. So what happens in general is some flux might link to one but not to the other. So some of those could be linked to the primary circuit, and similarly there would be a leakage from the secondary circuit. So therefore you have to worry about that. And this flux linkage in both parts of the circuit will lead to what is known as a self-reactance. I can reduce the effect by tight coupling. So what is done in tight coupling is, so you can reduce it by tight coupling. So what is done is to wind the turns of the secondary on the same core on which the primary windings are put. So that would make the coupling somewhat tight. The second assumption which is wrong is we have assumed that the resistance of the windings is 0, but that is really not true. So resistance of windings they are not 0. In other words, the transformer is never ideal. Let us suppose Rp and Xp are the resistances and the reactance of the primary circuit. And likewise, Rs and Xs are for the secondary circuit. Then I know that my impedance in the primary circuit is root of Rp square plus Xp square, and like this the impedance of the secondary circuit is Rs square plus Xs square. Now this will in turn mean that the induced EMF across the primary is not Vp as we have assumed, but is reduced by Ip times Zp. So induced EMF across primary windings is not Vp but reduced by Ip times Zp. Likewise, the voltage induced across the secondary windings and secondary is not Vs but reduced by Is times Zs. There are other effects which affect the transfer of power. Power transfer is never complete. There are many reasons for this. The first one is because of eddy losses in the iron core. This can be actually minimized by taking laminated elements, but this will lead to heating, which will reduce the amount of power transfer. And likewise, when you repeatedly magnetize the iron core, that is because you are passing an alternating EMF. So repeated magnetization and demagnetization, this leads to what is known as a hysteresis loss, which also result in heating and of course thereby reducing the power available. One of the losses is because of what are known as eddy current loss. So the point is this, that the core on which the transformer windings are put is made of metals. Now as this core is conducting, now as your current changes in the windings, there would be localized currents induced in this metal, because we would require them to oppose the changing magnetic flux because of changing currents in the windings. Now these are known as the eddy currents. You have learnt about it earlier. And this eddy currents will cause heating of the core, which of course naturally results in power loss. Now what do I do to reduce the effect of such losses? Now obviously we need to reduce the eddy currents. Now what we do in such cases, so to reduce eddy losses, we use what is known as a laminated core. I will explain what is a laminated core. See, what is done in a laminated core is instead of using a single block, I use layers of conductors which are glued to each other. So let me, roughly the picture is as follows. So this is my core. So let me show you a section of that. Now see, what happens here is this, that I take, instead of a single block, layers. So let me try to show you the various layers by trying to draw these layers. And of course, likewise, I have this section, and here my windings are there. So these layers or laminates, they are glued to each other by thin coatings which are insulating, and this helps reduce the eddy current because the thickness of individual layer being smaller, the available area for these currents becomes smaller, and as a result it reduces the eddy loss. So if there is a single block, then the eddy currents which will flow on the surface would be something like this. So this is eddy current. Now if instead we use lamination, because the surface area for each laminate is smaller, so that I have these laminates glued to each other by a non-conducting material. So the type of eddies that I will have would be something like this. So this is effect of lamination. A more artistic presentation of the lamination that one uses in transformer can be seen in the following slide. The other problem which we have talked about is due to hysteresis. Now we have seen that hysteresis arises because of the remnant magnetization. Now in order to reduce it, what is done, I will not be able to go through the physics behind it, but what is done is to use soft magnetic material, such as there are many materials with low hysteresis, and these are typically silicon steel, steel alloys, manganese, zinc, ferrites, etc. And these sort of are materials with properties which have less amount of remnant magnetization, and hence the hysteresis loss can be minimized by using proper material. So use of soft magnetic material with low hysteresis. Typically silicon alloys, steel alloys, silicon steel, steel alloys, manganese, zinc, ferrite, etc. Now in addition to the above losses, that is hysteresis and eddy, another loss is what normally goes as copper loss. This loss arises due to the resistance in the winding wires. So you notice that if the primary current is IP and the resistance of the primary windings is RP, then my loss in primary is IP square RP, and likewise the loss in secondary is IS square RS. So notice that both these losses depend upon the current that flows in primary and the secondary circuit, and so therefore such losses depend upon load. Now obviously we cannot completely eliminate the copper losses, but we can reduce copper losses is possible. And first one is fairly simple. You use very thick wires. So use of thick wires as winding wires. There are other engineering solutions is to keep the transformer inside high vacuum and pass high pressure varnish through the container so that all small holes are plugged. Suppose I have a transformer which has NP equal to 200 and NS equal to 10, and the supply voltage is 240 volts. Now clearly this is a step down transformer, step down by a factor of 20 because NP by NS is 20. So clearly my voltage, this is voltage in the primary is 240. So voltage in the secondary is 240 divided by 20, that's equal to just 12 volts. The current in the secondary can be obtained if I knew what is the secondary load. So load Rs, let me take it to be 20 ohms. So that should be simply 12 divided by 20, and that's equal to 0.6 amperes. How much is the primary current, assuming the complete power transfer? I know Is into Vs is equal to Ip into Vp. So that is 0.6 into 12 is equal to Ip into 240, which gives me Ip equal to 0.03 amperes. An important application of the step down transformer happens in power distribution or power transmission. Now, because of the fact that the power is produced far away from the cities which actually consume the power, there is a significant loss due to resistance of the cables, and the power lost is given by the current that is flowing times the resistance of the cables. Let me write it by RC. So RC is cable resistance. Now clearly my interest is to reduce this lost power as much as possible, which would mean that I want I to be, so reduce P lost implies that I should be as small as possible. Now remember that the power that is produced is actually I times V. So if I want small I for a given power, I want V should be as large as possible. So V should be large. But this is met with certain amount of danger because you are going to transport power at fairly high voltage. So what is done is that power is actually produced at a fairly high voltage. So let me talk about a typical power plant. So this is plant. So maybe let me take a small plant which produces, let's say, 20 kilovolts. Now what is done is that this is stepped up in order to reduce this loss. So I need a step up transformer. Suppose I make it some 200 kV or 300 kV, and then I transmit it. So this is transmission. This is where loss occurs. So cable loss. There are two steps in which it is brought down. There would be a substation in which it would be reduced to, let us say, 10 kilovolts. So this is step down. Once again, before it is given to the consumers, a further step down to, let's say, 230 to 240 volts as the case may be. Now this is a schematic diagram. So let us look at some numbers which will help us in understanding what's happening. So let us suppose I have a small power plant which is producing 1 megawatt of power. So power output, let me call it P out, from the plant is 1 megawatt, which is 10 to the power 6 watts. But that's equal to I times V. Power lost, we have seen, is I square times cable resistance RC. If you compare these two, I get a relationship between lost power to power out. That is equal to power out divided by V square times RC. That's very simple because this is I square. So I square is P out square divided by V square, and I have a P out here. Now let me take some numbers. Suppose my RC is taken to be small. Let me take it as some 10 ohms. And I have seen that my P out, the power output, was 10 to the power 6 watts. Supposing I produce V, power is produced at 20 kV. Then my power lost to power out is power out, which is 10 to the power 6, divided by V square. This is 20 kilovolts, so it is 2 into 10 to the power 4 whole square. RC I have taken to be small, which is just 10 ohms. If you calculate this, this works out to 0.025, which is a loss of 2.5%. Now if you increase the voltage 200 kV, you can repeat this calculation and find that this will give me 0.025% of loss. So what we have done today is to consider an important application of alternating current and voltage, that is its use in stepping up or stepping down the voltage using the principle of mutual inductance. And we have seen that transformers are of great practical use, particularly in case of power transmission, or whenever there is a need to either step up the voltage or step down the voltage from the supply that you have. With this, we come to the end of our set of lectures on alternating current. It is an appropriate time to summarize the content of this set of lectures on alternating current. So let's do that. So we started with a simple illustration of an AC generator, which consists of a rotating coil in a uniform magnetic field. As the magnetic flux varies with time, so will the EMF generated. And the rotating coil in B field, and the voltage or the EMF that is generated, will draw it as a function of time, and so it is something like this. Etc., etc. And this is the peak voltage. So I am plotting V as a function of time. This is time t equal to 0. And we also defined what was an RMS value of voltage or also current, and this was about 70% of that. So this is V RMS, and V was given by Vm cos omega t. The time period, which is this distance of time between a time t equal to 0 and the time when it again returned back to the same value of the voltage. So time period t, which is inverse of the frequency, is 2 pi over the angular frequency omega. This oscillating EMF also leads to an oscillating current. So I talked about oscillating current. Then what we found is that both oscillating EMF and the oscillating current, they may be represented as what we call as a phasor. After that, we are looking at what happens when we put in various elements in this circuit, and we found that for a purely resistive circuit, the current is always in phase. Current is in phase with the voltage. What it means is that if my instantaneous voltage through the resistor is given by Vm sin omega t, then the instantaneous current is given by Im sin omega t, where this Im is equal to Vm by R, is the usual Ohm's law expression. And we also defined what is meant by an RMS current by saying that I RMS is I maximum by square root of 2. The power dissipated P of t is I of t times V of t, and if you look at the average power, because each one of them has a sign variation, so that sine square of omega t, whose average value is half, will determine the average power, and that is equal to I RMS square times R, which is also equal to V RMS square divided by R. Having done that, we looked at a purely capacitive circuit. In this case, if the voltage across the capacitor is given by V of t is given by Vm sin omega t, then the corresponding charge, if you like, the instantaneous charge is given by C times Vm times sin omega t, and you can obtain the current by differentiating this, and the current at time t is given by Im times sine of omega t plus pi by 2. That is, the current leads the voltage by pi by 2. What it means is that the current peaks a full quarter cycle before the voltage does. So, I peaks T by 4 before voltage does. If you look at the phasor, then what you find is that because the current leads by pi by 2, so they would be on two consecutive quadrants of the xy plane. So, for example, let us take this as your V, then since the current is leading by 90 degrees, this should be your current, and so that this angle is 90 degrees. The value of Im is given by Vm divided by what we called as the capacitive reactance. So, Xc is capacitive reactance, and that is equal to 1 over omega c. In fact, Xc has a dimension of the resistance that is measured in ohms, and if you plot the Xc versus the frequency, so this is the way it behaves, because as omega is very large, the reactance is 0, goes to 0, and for small reactance it starts with infinite value. If on the other hand we have an inductor in the circuit, so inductive circuits, so this is the representation of an inductive circuit. So once again, let us take voltage to be given by Vm sin omega t. What we found is that the current is given by Vm divided by L omega times sine of omega t minus pi by 2, meaning thereby the current lags the voltage by pi by 2. And this maximum current that we have, Im, is Vm over L omega, and this quantity L omega is what is known as inductive reactance. Which goes linearly with the frequency, and if you are looking for a corresponding phasor diagram for this, then if this is where your voltage is, then the current would be in the preceding quadrant. So you notice that what we said is, for a capacitive circuit the current leads the voltage, and for an inductive circuit the current lags the voltage. We had given you a mnemonics which says Ellie the Iceman. Standing for that, for an L in the circuit, the EMF comes before the current does, that is EMF leads the current, which is the same statement as current lags the voltage, and for a C in the circuit, it is the current which comes before the EMF, that is current leads the voltage. Having done these individual elements, we discussed a series LCR circuit. In this case, the relationship between the voltage and the current was V is equal to I times Z, where Z is the impedance of the circuit, which has two components, a component which is in phase with the voltage, that is by resistance, and another component which is out of phase with the voltage, that is the square of the difference between the capacitive reactance and the inductive reactance, and by representing them as just x r square plus x square. In this case, if I again take V is equal to Vm sin omega t, the general expression for the current would be Im sin of omega t plus phi. This phi that is there may actually be positive or negative depending upon whether the a circuit is more capacitive than inductive or vice versa, and phi is given by tan inverse of xc minus xl divided by r, showing thereby that phi is positive if xc is greater than xl and is negative if xc is less than xl. So that if xc is greater than xl, the current leads the voltage and vice versa, of course. The power in the circuit, which is given by I times V, is equal to Im sin omega t plus phi into Vm sin omega t, and this on expanding sin omega t plus phi, we get two terms. The terms are Im Vm sin square omega t cos phi plus Im Vm sin omega t cos omega t sin phi. If you take the average of the power, then the second term that vanishes, because the sine function, this is essentially sine of 2 omega t, it vanishes, and we are left with only this term, which is Im Vm by 2, because sine square omega t has a average of 1 over 2 times cosine of phi, and this cosine of phi, we said, is the power factor of the circuit, which plays a very important role in transmission lines. The last thing that we did with respect to LCR circuit is to look at a phenomenon known as resonance. So look at the impedance expression, is given by R square plus XL minus XC whole square. Now for XL is equal to XC, Z has a minimum, and that minimum is R actually. Now if you tune in the frequency of the source, then the current would have a maximum when Z has a minimum. By varying omega, we get a maximum amplitude, At the same place where Z has a minimum, where XL is equal to XC, and that frequency turns out to be equal to omega 0 equal to 1 over square root of Lc. This is the resonant frequency. This occurs when the voltage across the LC part of the circuit is equal to 0. And what we found is that lower the resistance is, the sharper is the peak. So the pictures were something like this. This is against omega. So for high values of R has a rather flattish curve. As you decrease R, this is the type of things that you get, and further decrease of R gives you a still sharper this thing. This peak happens at omega equal to omega 0 equal to 1 over square root of Lc. So this is, let's call this R1, this is R2, this is R3, and this picture is for R1 greater than R2 greater than R3. It's just a graphical representation of the resonance phenomena. Normally this plot would be plotted not directly against omega but against logarithm of omega. It's a log scale, and in that what you find is corresponding to omega equal to omega 0, you will find there is a peak in the current, so that the current would become like this, and so this is omega 0, and so this is current, or current amplitude actually, and this is the variation of Z, the impedance. It has a minimum at the same place where the current has maximum. And if in the same plot I am also plotting the phase, so this is minus 90 and this is plus 90. So the way it does is the following. So this is your phase phi. So with this we conclude our series of lectures on the alternating currents.